Section 1.6, we're going to learn about two different kind of differential equations which require substitution, correct? So substitution methods, and one differential equation which is called exact. To begin with, let's talk about or define what they mean by homogeneous function of degree 0. Keep in mind not to be mistaken with homogeneous differential equation. These are homogeneous functions. A function fxy is said to be homogeneous if there is a positive real number like t, such that f of tx comma ty is exactly the same as f of xy for all positive values of t for which tx ty is in the domain of what? F of xy. So that's the definition of something called homogeneous function, not to be mistaken with homogeneous differential equation. In other words, in this particular case, let's say we have an example of fxy equals x squared minus y squared over 2xy plus y squared. The claim is this is a homogeneous function of degree 0. How do I do that? Replace the x's with tx, replace the y's with ty. So factor out the t squared from the top, which you get out of replacing these guys with tx and ty. And then you get t squared at the bottom, because this would be like 2tx ty plus what? Ty squared. So factor out the 2. These guys cancel. So you get what? The function itself, which is x squared minus y squared over 2xy plus y squared. Now, why is it called degree 0? Notice when you divide what? T squared by t squared, you get t to the power of 2 minus 2, which is what? Which is t to the power of 0, f of xy. So that's why it's called 0 degree what? Homogeneous function. Not all the functions are homogeneous. For instance, if you replace what? This guy with ty and this guy with tx, and this is not going to be equal to fxy regardless of what we do. So this is not a homogeneous function of degree 0 because when we replace the x's with tx and y's with ty and we simplified the fraction, which is not simplified, which you cannot simplify, and that doesn't equal to the original function. So this is not a homogeneous function. So if you have a homogeneous function of degree 0, then the derivative, the differential equation, is called homogeneous first order. In other words, this would be, this right here is called a homogeneous what? First order differential equation. So now what we have is the following. If that's the case, the idea behind the solution of what? Differential equations, which the function on the right side is homogeneous of degree 0, is as follows. You can somehow make this substitution, v is equal to y over x, and write the function on the right side as a function of what? V. If we let v to be equal to y over x, so y is equal to x times v, so if you take the derivative of this guy, and notice on the right side we have product of x and v, so we have to use the product rule, we get this. We substitute 2 back into 1, so we get something like this. So the equation becomes separable. Then we can solve the differential equation for v. Then we know v is equal to y over x. Then we can solve for y. So that's the idea behind solving what? Differential equations involving what? Homogeneous functions of degree 0. So now let's take a look at a solution and see how this guy works. So we have a function dy dx, differential equation, dy dx is equal to 3x squared minus y squared over 2xy. Is this homogeneous degree 0? I don't know. Let's check and see. In other words, this is what I mean when I say let's check. Replace the x with tx, replace the y with ty, so you get what? 3ty squared minus tx squared over 2 times what? Tx times ty. So this would be like 3t squared y squared minus t squared x squared over 2xy t squared. Factor out the t squared from the top, you get 3y squared minus x squared over t squared 2xy. Notice when you divide t squared by t squared, you get t to the power of 2 minus 2, and then you get 3y squared minus x squared over 2xy. So that will be 0. Do you see it? And this guy is the function itself. So this would be a homogeneous function of degree 0. Do you see it? Because these guys cancel. Correct? So we do have the right function on the right side. So we can make this substitution. That's what one of the type of problems which we make a tricky substitution to get the problem going. So in these kind of problems, we let v to be always to be equal to y over x. So 1 is homogeneous of first order differential equation. So this guy is a first degree. So what you do to put this in what? Y over x, you divide top and bottom by the highest value of or degree of the x. In this case, the highest degree of x on top and bottom is x squared. So you divide top and bottom by x squared. So you get 3y squared over x squared minus 1, because this guy divided by x squared is 1. And if you divide the denominator by x squared, you get this. Replace all the y over x's with v, so the equation becomes what? 3v squared minus 1 over 2v. So remember, we replace all the y over x's with v. However, the derivative of this guy, if you use what? If you kind of go y is equal to x times y, and you use product rule, so you go dy dx equals what? Derivative of x, 1 times v, plus derivative of v with respect to x, which is dy dx times x. So what you do in the original equation, you replace dy dx with what? V plus x times dv dx, and then this guy, the function on the right side, is 3v squared minus 1 over 2v. Move the v over to the right side and combine it with this fraction, and you get v squared minus 1 over 2v. As you can tell, the result now it's what? A separable differential equation. So divide, so right now I have x dv dx is equal to what? V squared minus 1 over 2v. Multiply both sides by the reciprocal of this guy and keep the dy on the left side. Divide both sides by x and multiply both sides by dx. So what we have done here, going from here to here, is called separation of variables. So we have separated the variables. So we force the equation, the differential equation, to be separable. So notice v's are on the side where dv is, x's are on the side where dx is. Now we are allowed to what? Integrate. When you integrate, on the left side, you get 2 natural log of what? V squared minus 1, correct? And on the right side, you get what? Natural log of x plus c. Excuse me. So because these two functions are what? Are logarithmic functions, So we will write what? C as natural log of C as well. It doesn't matter. Why? Because C is a constant, so it's natural log. Why did I do that? So I can use the properties of logs and say log of something plus log of something else is log of the product of the logrands. Do you see it? Now I will exponentiate. That means I would raise e to both sides of the equation. On the left side, I get v squared minus 1. On the right side, I get cx. But keep in mind, v was equal to what? It was equal to y over x. So now I replace v squared with y squared over x squared minus 1 equals cx. I solve for y squared, and lo and behold, this is the final answer, which is our what? Our solution to this differential equation. So this is one of the problems which we get to solve by using the special substitution v is equal to y over x. However, in order to do that, we need to make sure the function on the right side is a homogeneous function of what? Degree 0. Otherwise, this substitution will not force the equation to be what? Separable. Okay. The next one is called Bernoulli's equation, Bernoulli's, and they look like this. dy dx plus p of xy equals q of x. Notice without the y to the n, this will look like a what? Linear, first order linear equation. However, we have a factor of y to the n, where n is any real number except 0 and 1. Why can't n be 0 or 1? Because if n is 0, the equation becomes what? First order linear, which you can solve this by finding the integrating factor and go from there. However, if n is 1, then the equation becomes separable. Then you can move the y's over and kind of like factor, or you can move this guy over, factor out the y, and lo and behold, the equation becomes separable. How do you solve these kind of equations? Well, let's take a look at this equation. Y prime minus 1 over xy equals 4x squared y to the power of negative 1 cosine of x, where x is a positive number. Notice p of x is negative 1 over x. Q of x is what? 4x squared cosine of x. And this guy is my y to the n. So n is negative 1. Do you see it? So how do you do this? First thing first, eliminate this guy. How? Multiply both sides by y. In other words, multiply both sides of equation number 1, correct, by y. Because y times y to the negative 1 will what? Eliminate y to the negative 1 on the right side. So the idea is eliminate this y to the n on the right side of the equation right away. Once you do that, then you get this. Notice there is no more y to the negative 1 on the right side. Then you make this a special what? Substitution. Let u be this guy. Okay? Let u be what? The coefficient of the function of x on the left side, not the coefficient of y prime, but the coefficient of function of x. In other words, the coefficient of what? P of x. Do you see it? If u is y squared, then du dx is 2y dy dx. Okay, so so dy dx is what? 1 over 2y du dx, if you solve this equation for what? Dy dx. Incidentally, why do you let u be equal to this coefficient of p of x? Because the rule is let u be always equal to y to the power of 1 minus n. Remember, our n was negative 1 in this case. Remember, that's the power of the y on the right side, correct? So the idea is always let u to be equal to y to the power of 1 minus n, and that gives you y squared. Do you see it? You don't have to memorize this because, as I said, once you eliminate y to the n on the right side, then the coefficient of p of x, which is a function of y here, okay, let that be u. Take the derivative, solve the derivative for dy dx, and call that equation number 4. So substitute what? Equation number 3, equation number 4 into equation number 2. And that would be this guy here, which we obtain this by eliminating the y to the negative 1 on the right side, correct? When you do the substitution, you will end up with this equation. Half of du dx minus 1 over xu equals 4x squared cosine of x. Now this guy is a linear, first order linear differential equation. Okay, first you have to clear this coefficient by multiplying both sides of this equation by 2, so you get this. This is the standard form of a linear equation. So solve this equation for u. So solve for what? For u. How do you do that? Remember, this is your p of x. Find the integrating factor, which is e to the power of antiderivative of negative 2 over x dx. Okay, so the answer is e to the power of negative 2 times natural log of x, which is the same as e to the power of natural log of x to the power of negative 2, which is x to the power of negative 2, which is 1 over x squared. So now multiply both sides of this equation by the integrating factor. Remember, when you multiply what? The left side always becomes derivative of the integrating factor times the unknown function. But the right side, when you multiply this side by 1 over x squared disappears, so you just get 8 cosine of x. Now integrate, okay, both sides of the equation. The left side gives you what? 1 over x squared u. The right side gives you 8 sine of x plus what? C. So what do you do next? You, excuse me, kind of multiply both sides by x squared. So you get u is equal to 8x squared sine of x. Don't forget, when you multiply both sides of this equation by x squared, make sure you multiply what? C by x squared as well. So don't miss that, because sometimes students miss this. The answer doesn't come up right. But remember what we decided let u is. We decided let u be y squared. So replace this u with y squared. And now isolate y squared. Box the answer. This is our final answer. Do you all see it? Right? Finally, we have this kind of equation. Sometimes differential equation shows up like this. A function of xy called m, as in Mary, times dx, plus a function of x and y called n as in Nancy, dy equals 0. If you remember from multivariable calculuses, if you have a function of 2 variables, to find the total derivative, d phi dx, you need to what? Multiply d phi dx by 1, because partial derivative of this guy with respect to x is this. Derivative of x with respect to x is 1. Partial derivative of phi with respect to y is d phi dy, but derivative of y with respect to x is dy dx. So that's what you get. Multiply both sides by dx, so you get d phi is equal to this guy. Partial derivative of phi with respect to x dx, partial derivative of phi with respect to y dy. Compare what? This equation, this equation number 1 to 2. Looks like what we have is what? this kind of looks like the left side, and the left side looks like, and the right side is 0. In terms that we can conclude that kind of looks like what? The differential of phi is 0, or the derivative, I should say. If you integrate both sides, you get phi is equal to what? C. This is basically how the general solution of an exact equation should look like. It should be always what? A function of x, y equals a constant. So remember, C is a constant. So once again, comparing this form to that form, looks like partial derivative of my solution is m. Partial derivative of what? My solution with respect to y is n, because that's the coefficient of dy, and this guy is the coefficient of dx. So I got these. So m, the function which is multiplied by dx, is always partial derivative of your solution which you're trying to get your hands on with respect to x. And n, which is the function attached to dy, is always partial derivative of the solution you're trying to find with respect to y. So equation number 1 is called an exact equation if there exists a function phi, that's what it's called, such that partial of phi with respect to x is m, and partial of phi with respect to y is n. Incidentally, this particular solution, which is called phi of xy, sometimes in the context of other classes, this is also known as potential function, correct? Like in physics classes. So the question arises that how do I know, just because the differential equation looks like this, that doesn't necessarily qualify that equation to be an exact equation. So I need a test. What is a test? Well, we have a test, and the test is this equation is called exact if and only if partial derivative of m with respect to y is exactly equal to partial derivative of n with respect to x. So this is called test for exactness. Okay? Remember, not all the functions are exact. You know, differential functions. If they are not exact, then this procedure we are just about to learn won't work. For instance, let's take a look at this particular differential equation. 2x e to the y dx plus x squared y plus cosine of y dy equals 0. Is this exact or not? Remember, the function attached to the dx will be called m. The function attached to the dy will be called n. As you can tell, they both are functions on x and y, correct? Now, apply the what? The test, which is the partial derivative of m with respect to y, is it equal to partial derivative of n with respect to x? Partial derivative of m with respect to y, notice that 2x is constant, so derivative of e to the y is e to the y. Partial derivative of n with respect to x, e to the y is constant, so that guy goes for the right, but the derivative of x squared is 2x. And remember, y is constant because the partial derivative is taken with respect to x, so we keep the y's constant. So cosine of y, derivative of cosine of y is 0. So remember here, we keep what? Y's constant. That's how partial derivative works. Here, we keep what? X is constant. Do you all see it? As I said, not all the equations which they are written in this form are exact. For instance, take a look at this. 2x minus y squared dx plus xy dy, excuse me. So is the partial of m with respect to y This guy is constant. Derivative of what? Negative y squared is negative 2y. This guy is n, because that's the coefficient of dy. And the derivative, partial derivative of this guy with respect to x is just y, because what? Y would be constant. So negative 2y is not the same as y, so therefore it is not an exact equation. Excuse me. So as I said, not all the equations which are written in this form, excuse me, is called exact. You have to pass this test. So now the idea is, how do you go about solving these guys once you made sure what the equation is exact, correct? So if I take the partial derivative of x phi with respect to x, call it m, and partial derivative of phi with respect to x, call it n. So in this case, the partial derivative of m, the partial derivative of phi, which is my solution. Okay, that will be my solution. With respect to x is m, and with respect to what? Y would be n. Is that right? So there you go. Sorry about that. So here's basically what we do. We kind of take the partial derivative, let's say we take the partial derivative of, let's say, sorry about that, partial derivative of phi with respect to x, which happens to be m. Sorry about that. So here we go. So what we do, in order to solve this equation for phi, we kind of take the antiderivative, but we take the antiderivative with respect to x. In other words, we keep what? Y's constant. Do you see it? So therefore, the answer is what? Phi of x, y equals antiderivative of this guy with respect to x is x squared, but this guy is constant. But guess what? The constant of integration is not c anymore. Notice it's a function of y. Why is that? Because we kept the y's constant. Do you see it? Now, if we take partial derivative of equation number 1, which is what? Phi of xy is equal to x squared e to the y plus h of y with respect to y, we get what? X squared e to the y, because derivative of e to the y is d to the y, but the derivative of hy, which is a single variable, is h prime of y. In other words, this guy is just good old derivative with what? Of h with respect to y, correct? But remember, equation number 2 kind of looks like equation number 3, where partial derivative of the solution with respect to y is equal to n. In other words, partial derivative of phi with respect to y is this guy, which is n. So if you compare equations 2 and 3, they both represent the same partials. Can you see it? Partial derivative of phi with respect to y is this, and partial derivative of phi with respect to y is this function. So what we do, we set 2 is equations 2 and 3 equal to each other, and we get this. So x squared e to the y plus h prime of y equals x squared e to the y plus cosine of y. These guys cancel. So we get h prime of y is equal to cosine of y. Then we take the antiderivative. Remember, we take in the derivative with respect to y. So we get h of y is equal to sine of y. Because this is a single variable function, now you are allowed to what? Attach a constant, correct? So what you do now, call this equation number 4. Take equation number 4 and substitute what? H of y here. and then that would be your potential function. However, because I need what? One potential function or one solution, I don't need infinite many solutions at this point, or I should say one potential function. So what we do, set this guy equal to 0. However, the final answer always is what? Phi of xy is equal to what? C. So this is how the final answer should look like. Remember why? Because the derivative of phi was 0. So if you take the antiderivative, phi of xy has to be always constant. So take this, which is x squared e to the y plus sine of y equal to what? Set it equal to constant. And this would be, ladies and gentlemen, my final answer for an exact differential equation. Thank you.